this is the primitive definition, is base times height. BH. So area of a rectangle A is BH. Now, it's fairly obvious that this has to be the definition of the area of a rectangle. Because, first of all, suppose you had, let me just motivate this definition. These are the intuitive concepts, this is the basic definition. So suppose, you must have taught this too, suppose you have a unit square. So remember, there's a length which is called the unit length. This is agreed on by whomever. In some societies it's a foot, in some societies a meter, centimeter. Just say there's something called 1. You pick a unit, there's a length 1. But if you have a length 1, and since the Greeks could construct perpendiculars, they could make a square. That's not very good. So this is something, this is now a unit object in another dimension. So this is a unit rectangle, so to say. Okay, so what would its area be? A square unit. So you would say, well, this is a basic unit in this world of squares, so of polygonal figures. So the area of this has to be 1. So you make a definition. It's 1. Now, then you work away. If this is, let's say, height h, then how many units do I have along here? H units. And how many units do I have here? These are integers. Let's assume that h and b are integers for the moment, just to motivate the definition. If h is an integer and b is an integer, then you have b integers here. And now you can chop up the rectangle, okay? And each one into squares. So each one of these would be 1 by 1, 1 by 1, 1 by, well, because I'm not doing a very good job here. Forget my artwork. Every one is 1 by 1. Now, how many do you have? How many little squares do you have? You have b times h squares. Each one, by definition, has unit area, has area 1. So now we go over here and we look at axiom or intuitive idea, not just axiom, intuitive principle 3, the sum of the area of the parts is equal to the sum of the whole. So therefore, the area of the whole rectangle has to be what? The sum, which is you have bh of them, so it has to be b times h. So, from very basic principles, it's clear that this ought to be the definition, and you just take it to be a definition. That's how you assign area to a rectangle. Now, what the Greeks realized is that once you have defined the area of a rectangle and use these heuristic principles, intuitive principles, you can derive the area of almost everything. For example, you can, if you have a right triangle, so let's call this BH, then it has to have an area what? 1/2 BH. Why is that? So you claim, and because it's based on these intuitive concepts that somebody may not tell you, but it's the line of reasoning, the thread of thought that leads you to the formula. Because if area has these properties, then what do? I can duplicate this rectangle like this here, and this is now, this triangle is going to be exactly congruent to that triangle because you have side, side, side. It's a rectangle. So this triangle is congruent to that triangle, so if it has an area, then the area of this area here, area of the triangle, whatever it is, plus the area of the triangle, has to be the area of the rectangle, which is, by definition, this is a definition, BH. So therefore, you immediately realize that if there is an assignment of area, without actually defining area, that's important to realize. There's no definition in the classical literature of what area is. Everything is based on sort of this intuition. So you get that 2a is equal to BH, so therefore area of the triangle has to be 1/2 base times altitude, where the altitude is h. Now from this you can go to the area of another region. And that is any other triangle. And you use this principle over and over again. Suppose this is H, and now this is B. This is B. And I can call this A, and now this is B. And now we're building up more and more knowledge from very primitive knowledge, and I assume you do this when you teach these elementary things in class. Now, from the principle that this is the area of the whole is the sum of the areas of the things that make it up, which is our intuitive principle, then the area of this triangle, must be the area of this plus the area of that. And so this is a right angle, so the area of this is 1/2 AH plus 1/2, this is an H here, 1/2 AH plus 1/2 what? BH. But you can factor this is the same as 1/2 A plus B times H, but A plus B is exactly what? Big B. So you get the formula 1/2 base times altitude. Now from this you can build up the formulas of any sort of polygonal region, because you can break up a polygonal region into what? Triangles. And so you have, therefore, you can, in principle, the Greeks or anybody can now, like a puzzle, take any polygonal figure, whatever you want, just break it up into rectangles anyway. You, in principle, can calculate the area. Although in practice, it might be hard because you have to measure altitudes and so on and so forth. But in principle, calculating the area of something like this is very simple. Now, remember, by doing this, we are avoiding the actual definition of what an area is for general regions. Just so intuitive principles. And we're also avoiding, as the Greeks avoided, the definition of what a number is. Now, but then you come to a real problem, because remember, the Greeks loved perfect figures. I already told you that Xenophanes had argued that God was a ball. They also loved circles, because they're perfectly symmetrical. So now you have the problem of what is the area of a circle? What is the area of a circle? Now, when you proceed to try to answer this question, and you also don't have a definition of what area is, so you can't apply the definition to get the answer, you're also working on a sort of a set of beliefs. And it's a belief structure. And the belief structure says, well, it has to have an area, right? Because, you know, if you inherit a lot in Santa Cruz, and it happens to be in the shape of a circle, you believe that there's a certain content you have there. What exactly the content is, well, that's another matter. But you start off with a belief system that says the circle has to have an area. That's what the Greeks did. It has to have an area. The question is, what is the area? It has to have an area, even though I don't know what that means.
Why is that a belief? Why can that be derived from using the
Well, I'm going to talk about that. Because you have to, in order to derive the formula for area rigorously, based on logical principles. Now the Greeks were logical. You have to have a definition of area. You can't calculate something for which there's no definition. Now the problem with giving a definition of area, as we're going to see, the root of the problem, and the root of the logical difficulties, lie in the fact that they had no definition.